This talk will be is being recorded, and I would like you all to keep your mics on mute. But if you have a question, then just unmute your mic and go ahead and ask it. I'll also keep an eye on the chat in case there are questions, but just feel free to interrupt the speaker. Okay, so today it's a great pleasure to have Nate Harman from the University of Chicago, and he's going to talk about intermediate algebraic structure in the restriction problem. Over to you, Nate.
All right, thank you. Yeah, okay, so I want to, well, first, thanks for having me. I want to maybe warn everyone ahead of time that this is the first time I'm using slides in like several years. So I don't quite remember if I've got the pacing right when I was planning it. So hopefully that will be okay. Yeah, and then also, in many ways, this talk is going to be sort of an overview of a bunch of different kind of algebraic structures that arise in this one problem in combinatorial representation theory, and or at least they've sort of arisen in my attempts to solve this problem and understand what's going on. And I hope it sort of will shed some light on kind of what I think is happening in this problem. All right. Let me get started. So, oh, sorry. Oh, no, that's not right.
Oh, that's not.
Yeah, hold on. Sorry. Technical. All right, wait. Can you see this?
It's a little smaller, but if that's, yeah, that's fine.
Let me.
Good enough. Yeah, let's just go on. I think that's fine.
Okay. Yeah, I don't know what why that was doing that. Okay. So what am I talking about? So let me introduce some of the key players in this problem. So I'm going to talk about representations of general linear groups and representations of symmetric groups. But specifically, I'm going to be talking about polynomial representations of GLN. And so what are those? What do I mean by that? This is this condition that I think kind of in algebraic combinatorics, we kind of always assume that all representations are polynomial, but it's really kind of an extra condition. So I want to be kind of explicit about it. So the first one way of formulating it is that the matrix entries of the representation are polynomials, right? So if I put in a matrix from GLN, then I get out a new matrix in some other GL capital N now, and the entries of that new matrix should be polynomials in the entries of the original matrix. So that's one way of formulating it. It's also polynomial in kind of a different, maybe more categorical sense. These are exactly those representations that arise inside tensor powers of the defining representation. So by the defining representation, I just mean, GLN C obviously acts on n by n matrices, acts on, n-dimensional space, where it's just a matrix acts by itself. Right, so GLN is in a sense, defined as a representation to begin with. And so you can take tensor powers of that, and then you can look inside that and look for what representations arise inside that. And those are the polynomial representations. Or I should say maybe the irreducible ones all arise inside a tensor power of the defining representation. But if we want non-irreducible things, we might need to take direct sums. Okay. Another formulation or another condition that ends up happening is a polynomial representation of GLN always extends, or maybe is the restriction of, a polynomial functor from vector spaces to vector spaces. So this is kind of a nice property of polynomial representations, that as we vary the size of this vector space, this GLN, the n in GLN, they're kind of uniformly controlled by some larger category of polynomial functors from that really restricts to these representations for each n separately. I won't go too much into what this condition of being a strict polynomial functor is, but it's essentially you have a functor from vector spaces to vector spaces, and if you actually write out matrices for a map between two vector spaces, then the image of that map, the matrix that you get, again has polynomial entries, right? So entries that are polynomial in the original matrix entry. So this polynomial functor condition is really kind of just a categorical analog of the first condition, but now we're varying the size of the vector space. Okay, and then finally the last equivalent condition. So if I have a representation of GLN, it's polynomial if it extends from the group, the general linear group of invertible matrices to all matrices, right? So I can look at all n by n matrices, and under multiplication, that forms a monoid. That's a word that maybe we don't think about that often, but so there's an identity matrix, and there's multiplication that's associative, but we don't have inverses. That's what a monoid is. And these polynomial representations of GLN are sort of characterized as, within representations of GLN. These are the ones that you can extend over the matrices of not full rank, and we're gonna use that. All right, so feel free to stop me and ask questions at any time. I know that maybe this is not necessarily the same way everyone thinks of polynomial representations. All right, let's keep going. Oh, these are called polynomial representations. Right, fine. Okay, so the irreducible ones are called Weyl modules. I'll denote them W lambda or W lambda of n if I want to keep track of the n. What are these? Well, these are maybe the familiar representations. I know I'm talking to a algebraic-combinatorics crowd, so these are really kind of what everyone probably thinks of when they think of representations of GLN. So they're indexed by partitions with at most n parts. They're functorial in n in sort of the sense that I said. So this Weyl module W lambda is a Schur functor S lambda applied to this defining representation of GLN. And then what is a Schur functor? You can ask, well, a Schur functor is kind of the corresponding irreducible object in the category of polynomial functors. So, that polynomial functors together, they kind of behave like, you can think of them almost as representations of like GL infinity with some nice polynomiality condition. And so that's a kind of category. And these S lambdas are the irreducible objects or representations there. All right, but I mean, what's important is that as we vary n, we can really think of these W lambdas as being one object, as opposed to like a sequence of different representations of different groups. All right, maybe the most familiar thing for everyone is that the characters of these irreducible representations are given by Schur polynomials, right? And explicitly what that means when I say a character is I take a diagonal matrix, I push it through my representation, I have this phi lambda, meaning like the actual map defining the representation. And so you let your diagonal matrix act, and then you take a trace. And that trace, because of the polynomial property of these representations, that trace is just a polynomial in the diagonal entries. And that turns out to be a Schur polynomial. So that's, I think, hopefully in an algebraic combinatorics crowd, these sure polynomials are kind of familiar objects, things that we like. The size of this partition is the degree. It's also just the degree of the polynomials that appear inside the matrix entries, right there. Well, homogeneous polynomials even. So kind of, you know, agreeance of terms in different areas of math is always nice. So we have this notion of degree that shows up, and it's kind of what you expect it to be. On the polynomial functor side, this degree d is really controlling the dimension growth as well. So as we let n increase, this d is the kind of growth rate of the dimension. So the dimension turns out to be a polynomial in n. If we fix lambda and let n increase, it's a polynomial in n of degree d. Okay, and well, yeah, some lead coefficient that we can compute explicitly. Okay, so anyone have any questions or concerns thus far? We're gonna keep going.
Do the coefficients of the lower degree monomials in this expression, do they also have some sort of combinatorial interpretation like f lambda by d factorial?
Well, maybe that's something that we that I would like to better understand kind of in the context of this problem. So I will say this polynomial is actually you can write it as a positive integral, right, maybe non-negative integral combination of binomial coefficient polynomials. Right, so I mean, we know integer value polynomials can always be written as integer linear combinations of those binomial coefficients, but this is actually a positive one. So I don't know. I mean, I would say understanding what the actual coefficients are is very closely related to the problem I want to be talking about today. Yeah, I wish I understood them better. Yeah. Any other questions before I move on? All right, let's keep going. Okay, so that was kind of my introduction on general linear group representations, and I want to very quickly talk about symmetric group representations as well. So here, the irreducible representations are called Specht modules. I'll be using this notation S upper lambda to denote them. Now they're indexed by partitions of size n, right? So previously for GLN, we had partitions of length at most n, and now the relevant statistic is size, the number of boxes in your Young diagram, if you will. And then, of course, we can relate these to representations of general linear groups by Schur-Weil duality. And so really, you know, these labelings by partitions sort of match up in a way, but this is not the relationship I want to talk about today. So I always feel like I have to stress this because when I describe the restriction problem to people, they're always like, don't we know that? Isn't that what Schur-Weil duality says? And no, it's not. So this relationship in Schur-Weil duality that kind of links general linear group representations and symmetric group representations is great, but it's not the end of the story, or not the story that I want to be telling today. All right, so that's some basic stuff about the representation of symmetric groups, and like again, I'm hoping this is, you know, maybe familiar to an algebraic combinatorics audience, that, you know, if I start talking about symmetric group representations, I'm going to have things labeled by partitions. All right, but let's maybe something a little less standard. So if I have a partition of some size less than n, and maybe significantly less than n, I can build a new partition of size n by just adding a long first part. All right, so I imagine it as I have my partition as kind of a Young diagram, and I just stick on another row, and the condition that k is significantly less than n is just however small it needs to be so that this new row I'm adding is kind of the longest one. That's the condition. So we call these padded partitions. All right, why does this show up? So now, as n varies, these representations become functorial in a certain sense. It's kind of an analog of this theory of polynomial functors, but for symmetric groups. And this is made precise in the theory of FI modules. I'm going to talk a little bit more about this kind of in later on in the talk. But kind of maybe what really comes out of it is that you can really think of these representations S lambda bracket n as being one kind of object. They fit together to form kind of a single representation of S infinity, if you will. That's well behaved. So that's maybe the philosophy there. And then I want to point out that these irreducible representations of the symmetric group, again, their dimensions are polynomial in n, and there's this notion of degree, kind of, which is the size of this partition lambda. It doesn't really make sense to talk about it, in terms of a degree of some polynomial entries anymore, but it still controls this dimension growth. So that that formula at the bottom should look very familiar, and that's the same f lambda over d factorial that was in the previous slide. That should maybe be suggestive, but it's a different polynomial, I should say. This compared to the same polynomial formula that I had written down for the dimension growth of general linear group representations, this O of n to the d minus 1 really is different, but they have the same leading term. Okay, so that's a very short summary of kind of what you need to know about symmetric group representations to follow the rest of this talk. So all right, let me go on. So what is the restriction problem? So this is the topic of the talk today. The restriction problem and kind of algebraic structure that arises in it. And the point is, the symmetric group sits inside the general linear group as permutation matrices. A very natural action, kind of, or maybe even more natural, you can think of it as I have a functor from finite sets to vector spaces that is just the free vector space functor. So it sends a finite set to just the vector space of formal linear combinations of that set. And then this embedding of Sn is kind of exactly the action that you get from Sn acting on an element set sitting inside the corresponding linearization. So it's a very natural kind of subgroup to consider, beyond just the fact that it's kind of an easy thing to write down. It's natural in a kind of mathematical functorial sense as well. All right, so then what is the problem? So the problem is I want to understand the restriction of polynomial representations from GLN to this group of permutation matrices. Right, so I can take my irreducible Weil module for GLN and I can restrict it to the symmetric group, and then I can decompose it as a direct sum of irreducible symmetric group representations. And I mean, I sort of wrote this goal in vague terms because that can mean a lot of things. And of course, that can mean different things to different mathematicians. But for me, and for I think probably people in this audience, and for a lot of people in algebraic-combinatorics, what I really mean, what I really want, a positive combinatorial interpretation for these multiplicities. Right, so that is what I call the restriction problem. Kind of very concretely in algebraic combinatorics or combinatorial representation theory. Okay, so that's the problem. And now I want to talk about kind of what are some algebraic structures that arise in trying to study this. But maybe let me pause for a second. Does anyone want anything clarified or anything before I get into the meat of things?
What are the kind of mu's that appear in this?
In this sum?
Yeah, in this sum.
Yeah. Well, so what you should think is lambda has to be a partition of length at most n. So it has, at most n parts, and then mu is going to run over partitions of n, partitions of size n. So yeah, those are kind of the two conditions on these partitions that we have combinatorially. So these m lambda mu's should be defined whenever lambda has at most n parts and mu has size n. We'll see that these maybe that's not the best way to formulate it for as n varies.
A little more than that, maybe for certain values of mu, this is 0 or something.
Yeah, absolutely. You can ask which things actually appear, and that's kind of a subtle question. So I mean, even maybe the weaker question of understanding exactly when these m lambda mu's are non-zero. That's also a question that we don't understand. In completion, you can give some conditions, but it's hard.
Thank you.
Great. Okay, so let's go on. Okay, so first thing I want to talk about is the Rook monoid. So again, monoids, sorry. So what is the idea of this? So polynomial representations, these representations that we care about in algebraic combinatorics, I said it at the beginning, these are exactly those that extend over matrices of not full rank, right? So we have representation of GLN, but we can extend it to not full, kind of lower rank matrices as well. So then maybe the question to first consider is, well, what are like lower rank permutation matrices? What is the analog of that? And that gives us exactly this Rook monoid. So the Rook monoid is, we take n by n matrices which have at most one, so these are 0, 1 matrices, and they have at most one in each row and column, right? As opposed to permutation matrices, which have exactly one in each row and column. It's called the Rook monoid because you can imagine it's like a chessboard, and these correspond to ways of placing rooks on the board so that they can't attack one another. That's why it's named that way. So I like thinking of it just in terms of this matrix explanation. So it's these kind of partial permutation matrices, and then the operation is just multiplication. It's ordinary matrix multiplication, and again, this condition that you have at most one in each row and column is preserved by multiplying these, just like it is for permutation matrices. But maybe we can also define it, not in terms of matrices, if you like. So you define it as partially defined injective functions from an n-element set to itself. And what I mean by partially defined injective functions, maybe it'd be better if I called it injective partially defined functions. But what that means is partially defined function is you pick a subset of this set and then you define a function on that subset back into the set. So it's not completely defined. And then if you try and compose these things, maybe your first map sends an element somewhere, and then the second map doesn't send that thing anywhere. So the composition would just be not to send that first element anywhere. Right, and that is kind of exactly what goes on in terms of this matrix definition as well. Okay, so that's the Rook monoid. And the observation is that polynomial representations of GLN, because they can be extended to all matrices, they carry an action of Rn. I put restricted in quotation marks there because it's not literally GLN. You kind of have to restrict from the monoid of n by n matrices, not just the invertible ones. But it's a pretty canonical procedure. So these polynomial representations carry an action of the Rook monoid. Okay, so how does that help us? Well, we want to know what are the representations of the Rook monoid. And this was worked out originally by Munn, but then there's a exposition by Solomon where he kind of expands on that work and maybe makes it, pushes it a little bit farther. So what do these representations look like? Well, there's an easy construction. So you take a representation of some sk, right? So I take this irreducible representation S lambda. You can extend it to a representation of sk times Sn minus k by letting Sn minus k act trivially. So that's what I denote by this box times Sn minus k, right? So Sn minus k, that's the trivial representation of the symmetric group Sn minus k. And so that just means that I'm letting that component act trivially. And then we induce that up, that gives a representation of Sn. So that kind of says what it is as a symmetric representation. But it turns out that this induction, you can upgrade it to be an irreducible representation of this Rook monoid. So it's not irreducible as a symmetric group representation, but now you have these extra maps coming from the lower rank elements of the Rook monoid, and that turns this induced representation into an irreducible. Okay. As we vary lambda over not just all partitions of k, but as we vary lambda and k over all partitions of size at most n, these give us a complete list of the irreducible representations. And moreover, the representations are completely reducible. So everything is a direct sum of these. I mean, this part I find kind of amazing because complete reducibility is something we kind of expect from groups, but for monoids, you shouldn't expect it, but it happens. So that's a theorem. And then I want to just point out something relevant for us is this restriction from Rn to Sn is really easy, right? Because as I said kind of in the first part, as symmetric group representations, these are really just induced from this S lambda times something trivial. So it's just the Pieri rule. So restricting from Rn to Sn is, I think, sort of combinatorially easy. Okay. So one thing that this buys us, why I kind of want to consider this, other than the fact that it gives us more structure, is it defines us first a nice filtration on our representations. So what do we do? Well, okay, inside this monoid, there's an ideal. And an ideal means what you think it means. It means, if you multiply something in the ideal times anything in the monoid, you land inside the ideal. And so if we take matrices of rank less than R.
Can I interrupt you with a question, please?
Yeah.
Could you, that was a bit quick, the previous slide, the last statement.
Mm-hmm.
So just could you give some few examples of that? For example, if I took a partition of size n, of n, then it would probably restrict to the same irreducible representation.
Yeah, exactly. So if we take a partition of n, the
it-
construction is just you let all of the lower rank elements of the monoid act by 0.
Okay. And what if I take a partition of K which is strictly less than n? What would this work out to in terms of Sn? Just to, if you could give us one example.
Right. So if I look at this as a representation of Sn, if I look at inductions of this form where I'm inducing up from a product of Sk times Sn minus k, and I have my first partition is this lambda that we care about, and the second one is the trivial representation. It's a horizontal strip. So in general, these inductions, the multiplicities are governed by literal Richardson coefficients. But in the case where one of them is a horizontal strip, this is the simplest case. It's called a Pieri Rule. And so what it does is you take your partition lambda, which is of size k, and you add a horizontal strip to that partition in kind of all possible ways. And what you get on the Sn side is a sum over all of these spec modules corresponding to partitions that you obtain by adding a horizontal strip to lambda. So maybe very concretely, if we take lambda to be of size 1 and just a single box, what we would get would be, as a representation of Sn, would be a sum of Sn, the horizontal strip, the trivial representation, plus Sn minus 1, 1, and that you can recognize it as the ordinary permutation action of Sn on C to the n.
So there's a question on the chat from
Sorry, I can't see the chat.
So I'll read it out. Shraddha Srivastava wants to know what happens if lambda is the empty the empty partition of 0.
Yeah, the empty partition of 0. So what you get is ends up being a trivial representation of Sn. Yeah, so it's one-dimensional trivial thing.
Right. Okay, I think that's all questions for now.
No, lambda has to be a partition of K, right?
Yes, lambda has to be a partition of K, but K
So
can vary.
Yeah, I mean, lambda cannot be empty partition.
It
K can be 0.
Okay.
All right, let me keep going. So I'm going slower than I expected, but let me say one thing that this buys us is a nice filtration. I have these ideals that are kind of all of the kind of partial permutation matrices of rank less than some R. And so we get a filtration on any Rn module where we just look at kind of which vectors in the representation are killed by these ideals. Right, and really kind of just combinatorially, all this really is doing is taking these irreducible representations V lambda and picking out the ones of each size. So this kind of rank filtration exactly corresponds to just like the size of partition, statistic that we would think of combinatorially. But it's useful thinking of it in terms of these of which vectors are killed by this increasing chain of ideals, because that gives you something to kind of grapple onto when you're talking about these restrictions. And so in particular, one thing that you can just calculate with this in the context of this restriction problem is that the top term if I look at W lambda as a representation of the rank of the Rook monoid, the top term of the filtration is the irreducible representation labeled by the same partition. So that type of information is nice. But then the lower order terms are more complicated. You can figure out what the lowest term is in this filtration, where it just is everything. Yeah, so we get some information out of it. I would love to be able to understand the intermediate pieces, but you know, it's ongoing. It's difficult. All right, so that's kind of everything I wanted to say about the Rook monoid for right now. Although it'll show up again in a minute. So now I want to talk about representation stability and kind of the functorial nature of this problem.
Please show your previous slide for one more second.
Mm-hmm.
Thank you.
So I will say this filtration, there's a better filtration that'll show up later on in the talk that'll kind of refine this one even. So.
So these isomorphisms are of the Rook monoid.
Yeah, these are of the Rook monoid, I should say. So it's really the restriction of this W lambda n to the Rook monoid.
Okay.
Okay, so let me talk about the functorial nature of this problem and this representation stability. Right, so we saw that for general linear groups, the representations fit together as polynomial functors. And in particular, when I write down W lambda, I can really think of that as kind of a single object as n varies, corresponding to, well, in that case, a Schur functor. So what is the symmetric group kind of analog of these polynomial functors? And what can we say about them? So maybe the first thing to do is to reformulate what a representation of a symmetric group is in some sort of categorical language. So a representation of symmetric group is the same information as a functor from the category of n-element sets with bijections between them to vector spaces. So if you have such a functor, you just pick your favorite n-element set, that gets sent to a vector space, but since the n-element set, the endomorphisms of it are Sn, that vector space you get carries an action of Sn. And that completely defines the functor up to equivalence. So this is in some sense just a restating of what it means to be a symmetric representation, but kind of in the language of categories, which I'm sure everyone is very excited about. But why does that help? It motivates this definition of FI modules. So instead of looking at n-element sets with bijections between them, we can upgrade it to look at all finite sets with injections. So these are, this is a stronger, kind of fitting them all together in some sense. And this has gotten a lot of attention in recent years. This is kind of the cornerstone of the theory of representation stability. And it's sort of illustrated by this theorem of Church, Ellenberg, and Farb. So if we have a FI module, so there's a finite generation condition, which is important, but I don't want to kind of go too much into that. So we have a finally generated FI module. Then what you get is you get a sequence of vector spaces, one for each n. I mean, you get one for every finite set, but all that it really depends on up to isomorphism is the size of that set. So for every n, we get a representation of Sn. And then we can ask, well, what is that as a representation of the symmetric group? And the theorem is that the decomposition into irreducibles becomes independent of n, right? So here we have these padded partitions, lambda of n appearing, and these padded partitions, when we look at the decomposition into them, these multiplicities C lambda stop depending on n. Once n gets big enough, there's some sort of limiting multiplicity that takes over. So this phenomenon is called representation stability. And I mean, it was just defined by them maybe like 6 years ago or something. So it's gotten a lot of attention, and lots of things have been done in this area in the last 5 years. Okay, so that's, you know, a minute-long summary of the theory of FI modules, which I could, you know, go on for an hour. But I want to say that actually FI modules aren't even the end of the story for this problem. So something actually a little bit stronger happens. So these polynomial functors, we can restrict them, and they will give us finally generated FI modules. But FI modules aren't even as good as what we get. So let me restate everything. So if FI, in the language of matrices, is the category of based vector spaces, just mean vector spaces with an ordered basis, and then 0, 1 matrices with at most one in each row and exactly one in each column. So these are kind of injective. What I just wrote is really just a linearization of kind of finite sets with injections. But I want to kind of bring it back to this stuff about the Rook monoid I was talking about. We can do the same thing, just relax the condition on 0, 1 matrices so that we have at most one in each row and column. And again, I could define this in terms of partially defined functions between finite sets. And I personally like to think very concretely in terms of what are these as matrices. But so FI sharp, kind of the point is, if I look at just an n-dimensional, if I look at the n by n matrices, this condition just becomes the Rook condition. So this is kind of a version of the Rook monoid where now we are allowing sets of different size. We're kind of gluing the Rook monoids together for different n. And FI sharp modules are functors from FI sharp to vector spaces. So in particular, an FI sharp module gives us a representation of the Rook monoid for every n. And why I want to stress this is that these are way more rigid than FI modules. They just have much more kind of rigid structure, as I'll illustrate here. So these irreducible representations V lambda of the Rook monoids, they fit together into an irreducible FI sharp module. So sort of in the same sense that we can take the Vi modules W lambda of n for different n and those form a polynomial functor, these irreducible representations of the Rook monoid fit together into a single irreducible representation of FI sharp. Okay. Moreover, this is everything. These are all the irreducible representations of FI sharp. So nothing was missed in our sort of analysis of what happens for a single n. And and kind of even more amazing is that this whole category of FI sharp modules, which are sort of infinite chains of these representations glued together, it's semi-simple. There's a complete reducibility statement. And this last part is crazy. Like this sort of shouldn't happen, but it does. So we look at FI modules, this third point is just wildly false. Like typical finitely generated FI modules are not direct sums of irreducibles, and moreover, they're in fact infinite extensions of irreducibles. So it's a much stronger, more rigid condition to be an FI sharp module than an FI module. Another condition that I didn't write down, but maybe I'll just say verbally, is FI modules have they have an eventually polynomial behavior in terms of saying the dimension of the pieces of an FI module eventually becomes polynomial in n whereas fi sharp modules they're exactly polynomial. There's no eventualness to it. They kind of are polynomial on the nose.
Are the simple fi sharp modules the same as the simple fi modules?
No. So the simple fi sharp modules are these induced things. Fi modules are a little weird. So a simple fi module is actually just supported in 1 degree. So a simple fi module is actually just a representation of a single symmetric group. And so it's a little weird. So that, like as I said, fi modules, talking about finite length fi modules is actually not the interesting case. The kind of interesting behavior are all in the infinite length ones. So yeah, these are, yeah, it's really quite a different story.
So if I understand you right, the fi sharp irreducible modules are indexed by partitions of all sizes.
Of all sizes. Yeah, and they're very nice. They're all kind of combinatorially constructed by this induction. So you take your representation of sk, whatever size this lambda is, and then you induce it up to Sn by letting Sn minus k act trivially, and you kind of do that for all n uniformly, and it ends up carrying the structure of a Rook monoid representation, and an fi sharp, even stronger. So this buys you a lot. Being fi sharp is an unusual condition. Fi modules kind of just seem to appear everywhere in mathematics. Fi sharp modules are a lot rarer. And then the observation why this is relevant is that, I mean, the fact that this is relevant to the restriction problem is just a composition of 2 functors. So if I take my Schur functor defining my polynomial representations, and then I sort of pre-compose it with the free functor from fi sharp to vector spaces, which is really just sending, if you want to think about it in terms of sets, it's sending an n element set to the vector space spanned by that set. So this composition is saying that our restriction problem, our Schur functors, we can restrict them to fi sharp modules. So we see this very strong form of stability. And then, well, okay, the composition being finally generated is a fact that you need to check, but it's in the original Church-Ellenberg-Favre paper. All right, so that's all I wanted to say about representation stability for the time being. It'll make one more appearance, hopefully, if I get to it. But all right, so I want to talk about another approach, maybe closer to stuff that I've worked on directly. So first, if we look at diagonal matrices, so I write it as Tn, we call it, algebraic torus. So we can, alternatively, we can, restrict for representations from GLN to the torus. Seems fine. So, okay, irreducible representations of the torus, they're one-dimensional, and they're indexed by n tuples of integers that we call weights. And then polynomial weights are the ones where those n tuples are non-negative. And what am I saying explicitly here? So if I have a diagonal matrix with entries x1, x2 up to xn, then the if I have an n tuple n1, n2 up to n, n tuple of a1, a2, a3 up to an, then the irreducible representation of a given weight is just you let your matrix x1 through xn act by x1 to the a1, x2 to the a2, x3 to the a3, and so on. So it's a convenient and very simple group, and it has very easy representations to understand. And of course, we know how to decompose our irreducible representations of GLN as representations of this this torus. This is exactly what a Schur polynomial is. The coefficients of a Schur polynomial, the Koska numbers they're called, are just recording the multiplicities of each irreducible Tn representation that appears. All right. Why would I talk about this in this talk where I care about the symmetric group? Well, symmetric group sits inside the normalizer of this torus, right? If I conjugate a diagonal matrix, I get another diagonal matrix. And in particular, having an action on a group by outer automorphisms induces an action on its representations. In this case, Sn acts on the weights, and it acts in like the obvious way. If you have an n tuple and you act on it by an element of Sn, it just permutes the n tuple, the entries of the n tuple. All right, why is this helpful? This means that if we look at our polynomial representation W lambda, and we look at its weight spaces, Sn, it doesn't fix each weight space, but it kind of permutes the weight spaces in some orbits. And if we look at the sum over an orbit, that forms an Sn subrepresentation. So the point is, this torus is giving us kind of a grading, it's maybe like a multi-grading of our representation, and Sn preserves that, or kind of preserves it up to this permutation, which is relatively well understood. All right, so this is giving us another way of kind of breaking down W lambda further to maybe better get at what it is as a symmetric group representation. Okay, so this side, I'm just going to throw it all out here to begin with. So this is an example, and it's also why I'm sort of skeptical of symmetric function approaches to this problem. So I have it kind of color coded and broken down. But if I look at, so this is a Schur polynomial, S31, expanded out in the monomial basis of symmetric functions. But under this correspondence, these monomial symmetric functions, these are actually the characters of some subspaces that are preserved by Sn, right? And what I wanted to demonstrate in this slide, you don't need to know kind of, it shouldn't be obvious how I did these calculations. I spent an hour yesterday doing it. But what's important is these representations, they contain information about the symmetric group action that's just not apparent when we just write it as a symmetric function. So like this green term is really a sum of 5 different S4 representations, each with some different multiplicities. So what maybe one thing why I want to demonstrate is that, like, in my opinion, if you take symmetric polynomials too early, if we take the character kind of too early, we destroy all this information. So all of this information about how S4 is acting on these weight spaces is kind of not transparent when I just write it as a sum of monomials. All right, so kind of what I want to say, why I'm talking about the next thing is, I wanted to understand what these representations that appear in these generalized weight spaces, or these sort of sum over a weight space, sum of weight spaces over an Sn orbit, what they look like, and well, hopefully get that to solve the problem. All right, so that was sort of the motivation for why I did this next thing. So the idea is, I want to understand the action of Sn, but I want to do it in a way that respects this kind of grading it inherits from the torus action. So that leads you, I think, very naturally to consider the group of monomial matrices. So these are matrices that have a single non-zero entry in each row and column, and no other condition. And so why is this group so natural, in my opinion? Well, it is just the subgroup generated by Sn and Tn. So if I want to understand kind of both actions simultaneously, this is kind of the smallest thing that you can work in. It also turns out to be just the full normalizer of Tn. So maybe the philosophy is, well, if you want to understand kind of understanding a restriction to a group and understanding restriction to a normal subgroup are in some ways very different problems. Working with a normal subgroup kind of buys you a lot. So forcing this torus where we already understand this action to be normal is supposed to help. And then so we know what the structure of this group is. It's a semi-direct product, or you can write it as a wreath product. And wreath products are something where we really understand the representation theory pretty well, sort of as well as we understand the representation theory of both sides, which in this case is pretty well. All right, so one kind of consequence of this semi-direct product structure is that the irreducible representations of monomial matrices consist of a single sort of Sn orbit of weights for Tn. So really what was going on in that sort of last slide is each of those colors that I had was corresponding to an Sn orbit of weights. And then these monomial matrices were acting on each color kind of separately. All right, so that is why you might consider monomial matrices. How does it help us? Does it help us? Well, okay, what are the representations of monomial matrices? So it turns out the irreducible representations are indexed, irreducible polynomial representations are indexed by ordered lists of partitions, where now the total size has to be n. We know what the torus weights that occur are in terms of this combinatorics, and we know what the degree is. I mean, kind of what these things actually are isn't that important. It's that it's an easy combinatorial thing to work out. And we also know how to restrict from a representation of monomial matrices to the symmetric group. So it's again a form of a sort of induced module. And in particular, if you're interested in problems about giving a combinatorial interpretation for things, induced modules are easy. They give you Littlewood Richardson coefficients, and I would say we understand what that is well from a combinatorial perspective. So this last part is, I would just say, the point is it's something quote unquote easy in terms of finding a positive combinatorial interpretation. All right, I'm about out of time, so let me finish up this section. So I can say something, I have a little bit more restrictive class of representations called strongly polynomial. And this is where we have this list of partitions. And if the first one in the list is a horizontal strip, we call it strongly polynomial. And then in the notation, you just write as V of, again, this list, but you just drop the first one. And while hopefully it'll be apparent in a second why this is a reasonable convention. So theorem by me, I guess, I don't know. I am hesitant to even take credit. So the first thing to observe is that if I take a polynomial representation of GLN and I restrict it to Mn, it decomposes as a direct sum of these, let's just say strongly polynomial irreducible representations. So that's really where this strongly polynomial condition is coming from. It's kind of the relevant representations in this restriction problem. Moreover, we know what the Lie term is. So the leading term, so this W lambda contains this irreducible representation labeled by sort of the same partition, but now I'm thinking of this lambda as really a list of, it's, lambda 1, lambda 2, lambda 3, but lambda 2, lambda 3, and everything past the first one are all just the empty partition. So it's kind of all concentrated in the first position. And it contains this as provided n is bigger than lambda. Okay. Moreover, we can combine this now with representation stability. So all of these representations that I very quickly went through, these v lambda 1, lambda 2, 3, lambda, so on, of n, we can fit them together into a sort of FI module-like thing. So there's this category of, I wrote it as FI sub mon. And what it is you look at look at matrices of arbitrary size, where you have at most one non-zero entry in each row and column. So that forms a category under just normal matrix multiplication, and you can look at functors from that category to vector spaces, just like you would with FI or FI sharp. And the point is these v lambda 1, lambda 2, and so on form the irreducible representations, well, irreducible polynomial representations of now this larger category. And then the problem is now this kind of gives us a much finer grading on our representations, and we want to understand how they decompose. So I think I'll just wrap up here by showing the same calculation that I did for S4 previously, but in kind of this new language. And what I want to highlight is that I'm getting much sort of smaller and simpler expressions here, because I had these big sums of irreducible representations for the symmetric group, but really they're sort of coming from kind of larger representations of this larger group of monomials. And so that really simplifies this picture and lets you actually do these calculations. But all right, I think I'll stop there. I'm sure there's questions since I rushed through that last part.
I have a question. Could you please show us your next slide?
My next slide?
Yeah, or the last one, the way you had that here. Yeah. I would have thought from your description of FI sharp that is a monomial matrix analog of FI. But now you're saying FI mon is a monomial matrix analog of FI and FI sharp. So I'm a little confused.
So one thing that is nice. So if I look at either one, however you want to think of it as FI mon, because I have this, if I look at polynomial representations, so if I look at not just of FI mon modules, but if I insist that they have this polynomial condition, then they automatically extend to FI sharp as well. They automatically extend to the lower rank things, because being polynomial will force, you'll have like an x to the n type term, but then you can let x go to 0 to get the lower rank matrices. So it turns out that like there is a difference if I talk about kind of algebraic representations, whether I want to think of FI mon as an analog of FI or FI sharp. But if I think of just polynomial representations, you kind of pick up the lower rank things for free, because polynomials always kind of extend over 0, just by continuity, basically. So yeah, it's really kind of both. For free, you get the FI sharp part, sort of almost in the same way that you get, starting with a polynomial representation of GLN, it extends for free over the stuff with determinant 0. And it's that polynomial condition means that it has to extend. So yeah, so I mean, I think maybe the natural thing to consider for doing is you can write down a FI analog, a monomial analog of FI, but as soon as you impose this this polynomiality condition on the representations, they automatically extend to include lower rank matrices, and so you might as well think of it as a FI sharp analog.
Thank you. That clarifies.
What are the condition on the lambdas?
What are the condition on the lambdas
Yeah,
in this theorem?
yeah. No, I
Well,
mean, so lambda i's, can you permute the lambda i's when you say v lambda 1, lambda 2, lambda 3?
no, yeah. So it's very important for this v lambda 1, lambda 2. So let me kind of, I'll just say, so the lambda 1 term is a sort of degree 1. It's kind of a degree 1 term. Lambda 2 is a degree 2 thing. Lambda 3 is a degree 3 thing. I didn't say too much about it, but this notion, this is kind of encoded in how this torus weights are happening. So when I write down this sum of I times the size of lambda I being the degree, that's kind of indicative that like you count the first partition once, a kind of degree once, the second one degree 2, and so on. And that's also encoding kind of how the torus is acting. So maybe I can illustrate here. So I wrote down what it is as a representation of Sn. It's this induced module. But what you should think is, before we do this induction, my torus is acting, or I have sort of a smaller torus acting trivially on this part, acting with a degree 1 map on this part, acting with a degree 2 map on the S lambda 2 part, and so on. So yeah, so these different partitions are really, they're kind of happening in different degrees.
On one of your slides, you mentioned that the sum over orbits of weight spaces is a sub-representation of the symmetric group. Known about the decomposition of that sub-representation?
Sorry, what?
What is known about the decomposition of that sub-representation?
Well, so that's exactly kind of why I developed this machinery of monomial matrices. So this Casca module that I defined very quickly at the bottom of this slide is exactly what you say. It's we take an Sn orbit of weights, and that forms a symmetric group representation. It's actually a representation of monomial matrices because we have the torus acting. And so these are what I call Casca modules. And then really the problem becomes, how do we decompose these into irreducibles? And if we could answer that, that would solve the restriction problem. But these are, it's somehow we've broken up our module into a much kind of finer grading. And yeah, I would love to know what they are. But so here's my calculation for this degree 4 polynomial representation S31, and kind of in practice, it's fairly easy to kind of recursively compute these, but not in I haven't been able to figure out a sort of positive combinatorial way of figuring out what these are, but I have a list somewhere of things up to degree 6 or something that I just computed by hand. And so yeah, so these, when I write down this this K31, 11111, this is, I take the representation, the vi module indexed by 31, and I look at its weight space 11111. Okay, in that case, the weight space, there's a single thing in the orbit, but maybe a more illustrative one is if I look at the second one. So it's, I take my representation of GLN indexed by 31, and I look at the 2110 weight space, or 2110000, as many zeros as I want to make it of size n. I look at that weight space as well as all of its Sn conjugates. So it's all the weights that have a 2, 2 1s, and then a bunch of zeros, but in whatever order. If I sum over all of those weight spaces, that carries an action of Sn as well as the torus. So it's an action of M sub n, and this is its decomposition. So yeah, I mean, that's in some sense what the problem is reduced to, is understanding these Casca modules, which are sort of, I think of them as being sort of more categorical versions of these numbers. These Casca numbers that are controlling, that are just the coefficients in a Schur polynomial, actually correspond to the dimension of some module, or maybe kind of the rate of growth of some Fi sharp type object, and figuring out what those are is well, a thing I would love to do.
So you mentioned that the restriction functor to Fi sharp modules takes a strict polynomial functor to a finitely generated Fi sharp module. So Shraddha Srivastava has asked a question on the chat. She wants to know if this proof works in arbitrary characteristic, or do you use characteristic 0?
No, that works in arbitrary characteristic. So the point is, so finite generation, there's two properties of finite generation that are important. It's so one thing, it's closed under taking tensor products, two finitely generated things. Their tensor product is finitely generated. So in particular, if the defining representation forms a finitely generated Fi or Fi sharp module, so does its tensor powers. And then the second property about Fi modules that you need, that's also true in positive characteristic, is that finite generation passes to subobjects. So it's a Noetherianity condition where if I have a submodule of a finitely generated thing, it has to be finitely generated. And that's also true in arbitrary characteristic for Fi and Fi sharp. And so that lets you do it for polynomial functors, because polynomial functors are subquotients of tensor powers.
So you just prove it for tensor powers, and then
you just prove for tensor powers, and you need to prove this Noetherianity condition. I should say the Noetherianity condition is in some sense the cornerstone of representation stability theory, because it's kind of what makes every argument work for all the applications that they have. So that's a non-trivial step, but it's known for Fi modules over any Noetherian ring.
So if I understand what you're trying to say in this talk is that we want to understand the restriction all the way from GLN down to Sn. And so now you're breaking this up into smaller problems. So at the first level, we have a representation of GLN, and then you break it up into Kostka modules. Now that's pretty easy because it's just the Kostka numbers, right? And at the bottom, it's the monomial matrices to the symmetric group, and that's again pretty easy because it is just the Littlewood-Richardson rule. And so basically, you're saying that the hard part is this thing of Kostka modules to monomial matrices. Is that?
Yeah, well, I'm sort of just defining this Kostka module as, as a part of the representation that. Where the torus acts in a certain way, but yeah. I mean, the real difficulty seems to be in understanding how those decompose as representations of the monomial matrices.
I mean, that seems to be the only step which doesn't have a combinatorial answer right now.
Right. Yeah, that's the bottleneck, it seems. And yeah, so I've thought about this problem kind of a number of times in a number of different ways, and it always seems to really come down to the same problem of on these weight spaces, it's just not easy to tell what the symmetric group action is.
But your definition of Fi mon modules Okay, there's nothing wrong with it, but to me it somehow seems like cheating in the sense, well, I mean, you're just defining it, you're constructing this category out of monomial matrices, right?
Yeah, so I could be a little bit more kind of
Is
so
there
we
a,
actually have in the literature for FI modules and representation stability, there are things called FI sub G modules where G is usually a finite group, but it could be any group. So these are really kind of the same as FI sub C star modules, but with an additional polynomial condition.
okay.
So it's not really anything new. I mean, I would like to think of it as, I like to think of the monomials matrices as including ones of lower rank to make the FI sharp analog more clear. But again, if you have this polynomial condition, it kind of happens automatically. But yeah, this FI mon is really appears in the literature as FI sub G, or at least it's a special case of that. So it's something that people have studied. I mean, usually they take G to be a finite group, but C star is well behaved enough that the theory goes through there as well.
So I'm a bit not sure why there isn't an FI mon sharp. Is that redundant?
So it's redundant in it's redundant if we have this polynomial condition. So I could look at FI mon, and I could take kind of monomial matrices which are injective as my category for FI mon, and if I look at all representations of that, that will include things that are not polynomial representations kind of pointwise, right? So you'll be able to have, you know, kind of Laurent polynomial characters. But if I impose this additional condition that I want to only consider the polynomial representations, because that's kind of the relevant class of representations for this problem, if I look at polynomial representations of FI mon, then those automatically extend to the version where we include lower rank matrices. So kind of like if I look at all representations of GLN versus the polynomial ones are exactly the ones that extend to lower rank matrices. If I look at this FI mon or FI sub C star, if you like, the polynomial representations of that are exactly those that extend to kind of the FI sharp analog, which includes lower rank matrices.
Okay, thanks. I wonder if there are any more questions. We've had quite a few. It seems like there are no more questions. So I would request participants to unmute their mics and thank Nate for this talk.
Thank you. That was a very wonderful talk.
Yeah, I think it had a lot of new ideas, somehow very surprising ones, which I think get to the heart of this problem. So really, really great talk. Thanks.
Yeah, I should just say I really love this this restriction problem. I keep coming back to it, and it always feels like there's something more to grab onto. There's just so much structure hidden in this problem that I feel like I'm constantly noticing kind of new things to try and leverage.
Right. Yeah, I think you're not the only one. So yeah, Mike last week was similarly. Yeah. Oh yeah. So another thing I want to ask you: do you think there's any chance of explaining this? Sorry, we already clapped, but there's this paper of Asaf and Speyer where they prove an alternating sign thing. So do you think this approach that you have here would shed some light on that?
Yeah, so I was looking at that. I don't know. So my thought when reading that was that I think that's somehow related to some of these filtrations I was defining, like the one coming from the Rook module structure, or maybe the finer one. coming, but I don't know. I think it also one thing that is true about this problem is it's not just enough to kind of understand, or like, I kind of did the first part with this monomial matrices of saying what the representations are and kind of where they have to live inside it. But GLN, the fact that we have this larger group acting means that we have these additional maps kind of between the different irreducible SN components or MN components that are coming from this larger group. And I think it's those that are really going to kind of govern things like that. I don't know. I've read their paper and then thought about it a little bit, but I haven't been able to quite fit it into my framework. I mean, and sort of the same is also true about Mike Zabrowski's stuff, where it's in some sense a kind of orthogonal approach to this problem. And yeah, I would like to better kind of reconcile these different approaches.
Okay, so I think yeah, I'm done. So
I have one last question.
okay.
So you mentioned some universal enveloping algebra in your abstract, and
yeah. So I didn't get to that. I like I said, I haven't written a slide talk in a long time, so I think I got the pacing wrong. But yeah. Well, okay. So that algebra shows up in the following sort of subproblem. One of the things I want to understand about this restriction problem is the invariance, the symmetric group invariance. This is, asking what is the dimension of the SN invariance inside each polynomial representation is in some sense a subproblem, but it's also, I think, maybe the most important case. And so, how I wanted to think about that was, if I take a polynomial representation, irreducible, and I look at the symmetric group invariance, on the one hand, you think, okay, well, we just took invariance, so we've kind of killed all the algebraic structure. There's no more group acting, which is a problem. But what we realized was, if you look inside the universal enveloping algebra, right? So if we have a representation of GLN, the group, we also get a representation of GLN, the Lie algebra, and therefore it's universal enveloping algebra. There's the whole kind of subalgebra inside there that still acts on the invariance. So these invariants, the SN invariants of my polynomial representation, they're not just a vector space with no action on it. They have this sort of infinitesimal action of this subalgebra inside the universal enveloping algebra. And my hope that the sort of ongoing, so I've been working with a graduate student at UChicago a bit on this. His name's Josh Munninger. My hope is to sort of understand this algebra, kind of what its structure is as an algebra, and hopefully use that to construct something like a character formula, or understand certain kind of induction and restriction functors from that algebra to the full enveloping algebra. And it seems promising. I mean, we're making some progress. So that's maybe the newest stuff, but I didn't really get to it.
And you didn't.
Have you quantized this problem?
Did I quantize this problem?
Sorry.
I have not quantized this problem. Part of it is it's not clear what the right analog is. So if I know how to quantize representations of GLN quantum groups, but there's not then an action of the symmetric group.
Well, there's Hecke algebra.
Yeah, but the Hecke algebra quantizes the symmetric group kind of in the relationship between, like the relationship between general linear group representations and symmetric group via Schur-Weil duality is quantized via quantum groups and Hecke algebra. But the relationship where they're sitting inside one another doesn't get quantized. So there's not a copy of the Hecke algebra inside the universal enveloping algebra. So the restriction problem, at least at first glance, doesn't seem to quantize in a natural way.
So are you sure there's no copy, or it's just that there's no obvious copy? I mean,
there's no obvious copy. Yeah, it seems possible that there could be some way, or maybe not even a literal copy to restrict to, but you could just construct a functor that behaves like restriction in some other way. And I've thought a little about that, but there doesn't seem to be an obvious way to do it.
thanks.
So
Somebody
I
had another
wanted to
question.
ask that whether did you use the should-while duality in your talk today, or
I think not. Kind of avoided it. I mean, it shows you can reformulate some of these questions in terms of should-while duality. So for example, the restriction problem is equivalent to the following purely combinatorial question about representations of symmetric groups. So look at all functions from an n-element set to itself. So not bijections or just all possible functions from n-element set to itself. This set carries an action of Sn cross Sn, acting on kind of the domain and the range, pre-composition and post-composition. So if you linearize this set, right? So look at formal linear combinations. This gives a representation of Sn cross Sn, and if you could decompose that representation as a Sn cross Sn bimodule, or representation of the product group, that would be equivalent to understanding the restriction problem. And that equivalence is the statement of should-while duality. So I think, so that's one way that you can use should-while duality to try and understand this restriction problem. But I think in the stuff I talked about today, it doesn't really show up.
okay.
Okay, so it looks like there are no more questions now. So thanks a lot, Nate, and thanks for your patience. And thank you all for coming to the seminar. We still haven't decided on a speaker for next week, but that will be up on the website before then. Thank you.
Bye. Thanks for having me.
Bye.